Hey everyone, so this section is going to be about solving inequalities and using interval notation and then graphing on a number line. So first topic we're going to look at is using interval notation to express solution sets and then using a number line to graph solution sets. Those two kind of go together. And then after that we'll solve linear inequalities in one variable. This is really similar to what we did in the first chapter of solving linear equations in one variable. Inequalities have one spot where they're different. I'll point that out when we get there. And then our solution sets are going to be things like, instead of x equals 7, it might be all x's that are greater than 7 or all x's that are less than or equal to 7. So we'll get sets of solutions instead of just single values. A little bit of notation to look at here. Less than, greater than, less than equal to, greater than equal to. Hopefully those are familiar from previous math existence. When we're using less thans or greater thans, when we get to the graph, we're going to use an open dot to indicate that that endpoint on our graph isn't included. When we're using equals to, our graphs are going to have solid dots on the endpoints, and that's to indicate that the endpoint is included. So equals to solid, no equals to open. The other thing in terms of interval notation, when we're using less than, greater thans, and open dots on our graphs, you'll see what I mean by this in a second, but we're going to use parentheses when we're describing the endpoints there. So parentheses go with open dots, go with no equals, and then when there isn't equals, we're going to use brackets. So it's brackets, solid dots, and equal signs. We're also going to see we're going to have some negative infinities and infinities in our solution sets, and infinity always gets parentheses. There's this other thing in the box here. When you multiply or divide an inequality by a negative number, you need to reverse the direction of the inequality. I'll show that in a second when we get to a problem that actually does that. So for here, there's a couple of different terminologies, and let me point those out as well. So when we're talking about things that look like this is called inequality notation, and it has that right here, but that's where we're using the inequality symbols. Interval notation is where we describe the interval by starting on the leftmost endpoint of the interval and then ending on the rightmost endpoint of the interval. And that's going to be where we're using infinities and these parentheses or brackets as appropriate. So for this particular problem, let me get my pen set up because I never remember to do that ahead of time. It's asking us to describe this in interval notation. So this would be, we start with interval notation on our farthest to the left, and farthest to the left here is going to be negative infinity. If we kept going forever, that'd be negative infinity out this way, positive infinity out this way, and that's going to go up to negative 4, but not actually include negative 4. So that's where I want to use a parenthesis because there's an open dot instead of a closed dot. When there's a gap in the graph like this, we use a symbol that looks like kind of a capital U, and it's called union, and it's a way of saying this part over here or this part over here. So that's how we paste two separate intervals together. And our next point that counts is going to be negative 3. That one has a solid dot, so I'm going to be careful to use a bracket. And it's going to go up to and include 0, so again, another bracket. So you can see for interval notation, we're just using the endpoints at each spot to describe the interval. You have to be really careful with the parentheses and the brackets and the commas and then the order. This is the only correct answer to this graph. If you reverse it and say from 0 to negative 3, that would be wrong. If you had parentheses, that would be wrong. So it has to be pretty precise here. Start on the left, work to the right, and then use those endpoints to describe each of the intervals. So that was from a graph. This next one is basically the same thing, but it's asking us to, again, express the answer in interval notation, but it's, instead of a graph, it's giving us inequality notation. So if you're having a little bit of a hard time kind of getting your brain orientated on that, something that can be really helpful to do is to just draw a quick and easy, not terribly accurate number line, just to kind of organize your lefts and your rights from each other. Careful to put the small number on the left and the big number on the right. And then this reads x is less than or equal to negative 3. So since there's an equals to, let me put a little dot there. And that means my graph would be going this way. And then x is greater than or equal, or not greater than 6, not equal to. So there I want to be careful to use an open dot if I were going to graph this going this way. Again, you don't have to draw the graph, but it's kind of helpful for writing the interval notation when you're first getting used to this. So we would start out here at negative infinity. Again, the infinities always get a parenthesis because we can't ever get there and include it. And that's going to go up to negative 3. We'll use a bracket on that one because of the equals. And then we'll have a union because we have a gap between our solution sets. We pick back up at 6, parenthesis there because of the open dot and no equals. And on out to infinity from there. And so that would be our solution set in interval notation. And what we'll see as we go on to the inequalities here in a second is they can ask for the answer in either of these forms. You just have to be a little bit careful when you're reading the directions to make sure that you're answering. Do they want inequality notation, which we have here, or interval notation, which we have there? On quizzes and exams, I almost always ask for interval notation, so just a little heads up there that that's kind of the one that I prefer. I think it's a little bit cleaner to work with. Number 6, so this is getting into this third point here where we're going to solve linear equations in one variable. Let me go ahead and talk about why when we multiply or divide by a negative, we have to reverse our inequality. So let's say I have 2 is less than 3. That is a true statement. 2 is absolutely less than 3. Let's say I multiply both sides of this by negative 1, because for some reason that is useful for me to do. And when I'm working on an inequality or an equation, as long as I do something to one side, I have to do it to the other. But it's legit to do that. And we'll see that we do end up multiplying or dividing by a negative frequently. So that would be negative 2 is less than negative 3 if I did this wrong. If we think about a number line, 1, 2, 3, there's 2 and 3. 2 was really less than 3, but 1, 2, negative 3. Negative 2 is not less than negative 3. When we flip over to the other side of the number line, the numbers that are smaller in terms of their absolute value, so 2 is smaller than 3 if we're thinking of walking this distance, those are actually to the right. They're actually the bigger number on the negative side because they are less negative. So when I multiply or divide by a negative number, I have to be careful to switch the direction of the inequality. And that is the only thing that's different from chapter 1 in terms of solving these. Everything else is going to be the same. And I'll show you where you can spot that that's going to happen. So for solving this, if we thought of it just as an equal sign, the first thing we would do is subtract over that 6. We'd undo our add subtract first and our multiply divide second. Nothing has changed. So we will subtract 6 on both sides. Notice I am not multiplying or dividing there. I'm subtracting, so there is no sign flip. So that's going to be a negative 9. And then I would divide out the 3 on both sides. And that would give me x is greater than negative 3. So it's right there where I'm multiplying or dividing. In this case, it's division. I divide it by a positive, so there's no flip on this one. And I end up with x's that are greater than or equal, or not greater than negative 3 are going to keep this inequality true. So I'm supposed to graph the solution on a number line and give the answer in interval notation. Okay, so negative 3 would be right there. I'm going to use an open dot because of the no equals. And then my line would go that way. Here's kind of a dumb way to make sure that you're getting these in the right direction. If you think of that inequality sign as an arrow, it does tell you which way the line's going to go. It's better to be able to read this and say x is greater than negative 3 and know that's to the right, but just as kind of a dumb little way to make sure you're heading the right direction, inequality should face the same way as the arrow. Back here, just to show that was the same thing, x's were less than or equal to negative 3, so there's my arrow, there's my inequality. X's are greater than 6, so again, my arrow and my inequality. The last thing I got to do there is give my answer an interval notation. So this is starting off at -3, and it's going forever to the right, so that's going to go to positive infinity. And again, remember with interval notation, you're always working from the left to the right, from the smallest to the largest, and the order that you write that in, if you write infinity to -3, that would be wrong. You always got to go left to right. So for number 7, same basic thing. Let me rewrite that down here just to make it a little bit easier to work on. So we want to get x's to one side and numbers to the other. We can do that in 1 step or in 2 steps. I'll go ahead and do it in 2 steps on this one. So arbitrarily I'm picking the numbers to work on first, and then since I'm bringing my numbers to the left, I'm going to end up bringing my terms of variables to the right. So this will be -3x is greater than or equal to 4x. 7 minus 28 would be -21 right there. And then right here, this is where I'm going to bring this 4x over to the side because I want to get, again, x by itself. So now I have -7x is greater than or equal to -21. So that is the spot where we're going to divide by a negative. It's usually going to show up on this very last step. And the 7 right there is a -7. So when I divide both sides by -7, that's where I'm going to have to flip the direction of the inequality. So look for negative numbers as coefficients on your x terms, and that's kind of your heads up that that's about to happen. So this would be x, and now it's less than or equal to +3. On my number line, so x less than or equal to +3, that would be a solid dot because of the equals, and our graph's going to go that way because the x's are less than that value. So for our interval notation, we want to go from -infinity up to 3, and then because of the solid dot, we're going to be careful to use a bracket right there. And that's pretty much it. And then these remaining ones are just kind of reminding you where they get a little bit more complicated bits to them, but it's all the same thing. For these last 3, they didn't ask for a graph. So let's just run through these and make sure I remember how to solve them from the first chapter. So for there, I'll distribute that negative through. So that'll be a -3x, and negative would be a +48 plus 9 less than 6. So right there I'm kind of noting I have a -3x, and that means when at the end of the problem, when I'm getting that x by itself, I'm likely going to have a flip right there. I really strongly encourage you to collect terms before you start moving stuff around, same as in the first chapter. And the reason is that's just kind of where everyone makes the errors, is when they're moving stuff back and forth. So it's better to go with your 48 plus 9, get that simplified down as much as you can before you start moving things around on either side of the inequality. So we'll subtract 57 on both sides here. Boom, boom. That's going to leave us -3x is less than -51. And then there is where I am dividing by -3. So again, once we see that, be suspicious that this is probably coming up. So that cancels, and then x is, remember to flip that, greater than, and 3 goes into 51 17 times. And this one is asking for inequality notation, so that's exactly what I have right there. So that would be done. And I think that's the directions for these last 3. Yep, I didn't put new directions, so that would be it. Same basic ideas, so 3x, and then plus 15 minus 5 less than -5x plus 9. So with inequalities and likewise with equations, we can solve the x's to either the left or the right. It doesn't matter. We'll get the same answer either way. When I'm working with inequalities, I almost always solve them to the left. And the reason for that is, let's say I have, x is, that's a terrible greater than, x is greater than 5. If in this order, I think it's easier for people to see that means if I was going to graph that on a number line, there's 5, and we're going that way because the x's are bigger than 5. Another way I can write this is 5 is less than x. Those mean the exact same thing. This still says x is bigger than 5, but when you write it in this backwards order, I think people get messed up as to which way that solution is. So that's why with these ones, I'm almost always going to bring the x over to the left-hand side just because I think it's easier to read the solution set when I do. So holding with the plan that we want to collect everything we can before we move stuff left or right of the inequality, let's rewrite this as 3x, 15 minus 5 would give us a 10 right there, less than negative 5x plus 9. And then I'm going to do this one all in one step just to kind of show that. So let's bring the 5x over, and let's bring this 10 over here. So I'm getting my x's on the left-hand side of the inequality and my constants on the right-hand side. And if you're more comfortable doing that in 2 steps, by all means use 2 steps, but there it is in 1 step. So 3 and 5 would give us 8 x's. The 10's canceled, that was the plan. The 5x's canceled, that was the other plan. And that's less than 9 minus 10 would give us a minus 1 right there. Dividing the 8 over, I have x is less than negative 1/8. There is no sign flip on this. This is a negative number, but I divided by a positive, so that means I do not need to reverse the direction of that inequality. And this last one is pretty similar to those, just a couple extra steps again. So negative 13x plus 10. And before you get too worried about this negative 13, you kind of want to see where it ends up when I get the x's on this side. So it's currently a negative, but it may be when I combine my terms. It won't be by the end. So here we're going to have negative 3x. Negative 2 times 6 would make negative 12x. And negative 2 times negative 1, careful with that sign, is going to make a positive 2. Again, I like to collect my like terms before I move stuff left or right. And so minus 3 minus another 12 would give me minus 15x right there, and plus 2. So then we will add our 15x over, and then end up with 2x, so we won't have a negative on that to worry about. And then let's move our 10 over, so this is just doing the same thing as I did on the last one, but with 2 steps instead of 1. So 2x is greater than or equal to 2 minus 10 would give us a negative 8, and we'll divide out that 2 on both sides. So we end up x is greater than or equal to negative 8 over 2 would give us a negative 4 right there. And again, it asks for inequality notation, so for these last examples, I don't have to write the interval. Hopefully that helped with inequalities in